So thank you for the invitation. For me, it's a great pleasure and honor to be here, invited to this great conference with great people. And I thank a lot Peyton and Bary for inviting me to the event. So I forgot to put my affiliation. I will come back to it at the end of the talk. So I'm coming from Moroccan Center. It's a new center, Moroccan Center for Game Theory in Rabat, Morocco. So if you want more information, ask me. So the guy who is giving microphone to speak is postdoc in my center, so he can also speak about it. And Peyton was visiting me last year. So just to say that game theory now is expanding to Africa. So my co-authors, Hari Govindan and Luca Pal, to whom I'm very, very grateful because they did many of the work that I'm going to present. So it's really a joint paper with these two great authors. So it's about Nash equilibrium.
You have to point to the computer to make the slide.
I should.
And then for the pointer.
So the starting point was a conference in honor of Reynard Selten. And there was a special issue by Roger Meyerson, wrote a paper on this called Sustainable Equilibria, which is kind of the origin of this work. It's about refinement of Nash equilibria. So he was asking himself, trying to guess what should be the principle that you want to have to select amongst the equilibria. Many principles, like it should be intuitive, okay, but also it should satisfy some invariance properties, and it should exist in the class of game that we want to have as a class of game. Then he gives the battle of the sexes as an example. So we'll see an example of the battle of the sexes. And he ruled out the mixed equilibrium in the battle of the sexes and selects the pure equilibria as the good equilibria. Okay. And sorry that it doesn't work very well. Then he discarded some concept of refinement that rule out the mixed equilibrium in the battle of the sexes, like Persin's equilibrium of Calais, because it failed invariance, and ESS of Miner-Smith because it's failed existence in every game. So then he moved on, and he said, okay, let's look at topology and fixed point theory. If in fixed point theory you can classify equilibria or fixed points, give them index, plus minus 1, and perhaps we can come up. So let me give an example. If you take a function going from minus infinity to plus infinity, it will cross the x-axis in several points. When it's positive increase, call this plus 1 index. When it's negative slope, call it a minus 1 index. And then Meyerson was wondering whether we can classify the sustainable equilibria by this index. Can we associate an index to each equilibrium? Can we say that sustainable would be plus 1 and unsustainable would be minus 1 index? Okay. In fact, the paper of Meyerson was published in 95. In 92 and 94, you had already some people in game theory, Ritzberger and Gould-Pierce-Tachetti. They define index for equilibria in games. I will come back to this. Just to give the relation between fixed point and index. In the image on the left, you have a function from 0, 1 to 0, 1. It will cross the diagonal. If you take the identity minus, so the identity is a diagonal. If you take identity minus f, it's called the displacement map. So we have the figure that we saw before. And it gives you the idea that you will cross the diagonal, generically speaking, an odd number of times, and you will have n. If you have two n plus 1 equilibria, n plus 1 would be plus 1, n would be minus 1, and so you can. And the index will be the sign of the determinant of the Jacobian of the displacement map at the 0 of the displacement map. So this is roughly speaking what Meyerson did. Then Meyerson said, okay, I didn't define anything formally, but yeah, he gives the principles. But then Hofbauer who is a great game theorist working on dynamics. So the famous book with Hofbauer and Sigmund, formulate what should be sustainability in general. So the principle, let's put A1 like axioms, but of course, so you can see them as axioms or principles or desirable properties that Mersenne wanted to have. So A1 would like strict equilibria to be sustainable. We would like in the battle of the sexes, only strict equilibria are sustainable. And we want a game that has a unique Nash equilibrium. That Nash equilibrium should be sustainable. So somehow we want existence in every game. So if the game has only one Nash equilibrium, if we want a general theory which exists in most of the game or all games, we want to have existence. So perhaps we will not have existence in every game, but let's at least ask existence in a large class of game, regular games. Regular games is an open dense class of games. So I would like existence to be true in almost every game, let's say. And the most important property, I will call it invariant. So the addition or removal of inferior replies. So this is a kind of independence of irrelevant alternatives condition. So if you take your game, take one of the equilibria of the game, you will have many. And now you delete or you add strategies to the game that are not best reply to the equilibrium. So if you say if your equilibrium is sustainable, it should remain sustainable in the game where you add this strategy or you drop this strategy. Okay, so it's kind of a strong notion of forward induction, if you know about refinement theory and forward induction. So in forward induction, and the principle of forward induction by Goldberg and Mertens, they want the component of equilibria to remain, to not vanish if we delete non-best replies. Here we want to be exactly the same. Doesn't change if you remove inferior replies or we add inferior replies. Okay, so it's much stronger notion of forward induction. So what is our definition of sustainability? So it will be defined on the correspondence of the game, meaning the graph of the game, meaning a game and an equilibrium of that game. So take a pair. The pair will be a game and an equilibrium of that game. And we are going to say that two pairs are equivalent if I delete in both of them all non-best reply to the equilibrium, I have two identical games after relabeling of the strategies. Okay? So if I remember my two axioms, independent of relevant alternatives and uniqueness imply sustainability, then if I manage to find an equivalent pair in which an equilibrium becomes the unique equilibrium, this equilibrium should be sustainable, necessarily. If I take a game and I manage to add strategies to the player that are inferior replies to the equilibrium, at the end I have a game which has a unique equilibrium. In this larger game, this equilibrium should be sustainable because it's unique. So now if I remove all strategies that are irrelevant alternatives, it should remain stable or it should remain sustainable in the smaller game. So I cannot, all equilibria that can be made unique somehow cannot be removed in any theory of rationality if we believe on the III axiom. Then Hofbauer cleverly combined these two axioms by using some kind of minimality, and he defined the set of sustainable equilibria to be the equilibria that can be made unique by adding inferior replies or dropping inferior replies. So let me give an example. Battle of the sexes.
Elimination is one step, not iterative. I want to make sure I understand.
I'm going to give another definition that you will understand, but I give an example, okay? Now I'm going only to add strategies, in fact. In this paper, in this presentation, I will never delete, I will add strategies. The game will remain the same game, but I add strategies to the game, okay? But in the original definition of Bary, you can delete and add. So now to take the battle of the sexes, let me try to make the strict equilibrium unique. we can do this easily. How? I add a strategy, a row X and a column Y. This strategy will kill anything but the equilibrium I want to keep in red. So this payoff is strictly less than this one, but higher than, imagine I have other rows. I can eliminate all the other rows by adding one strategy that kills everything else. I can do the same for other player, and once I eliminate the strategy that I don't want to keep, I can manage such that X and Y themselves become strictly dominated, and now I have a game which is even dominant solvable. Okay? So the strict equilibria can be made unique very easily. However, the mixed equilibrium cannot be made unique in this game, and I let you think about how to prove it. It is impossible to add strategies to the player in this game that can make the equilibrium, the mixed equilibrium in this game unique. Impossible. You cannot add strategies that are inferior replies, add 1 million row, 1 million column that make the equilibrium unique. So how can you prove that? Not easy. So now I give you our definition of sustainability. A Nash equilibrium is sustainable if it can be made the unique equilibrium of a larger game obtained from the original game by adding inferior replies to the equilibrium. So now I will not delete anything. Okay? So let's do it even. So with this, now we can make infinite game all strict equilibria sustainable using exactly the same construction I did. And now we can ask the question, okay, in the previous game, the mixed equilibrium was not sustainable in the sense of this definition. Can we have other games where the mixed equilibrium can be made unique? And there is such a game. Take the coordination game, this one. All the equilibria of the diagonal can be made unique because they are strict, but this game has 7 equilibria. The pure one in the diagonal, the mixed where you mix between two actions, and the completely mixed 1/3, 1/3, 1/3. Okay? So, Van Stengel, his PhD student, proved that in this game, you can make the completely mixed equilibrium unique by adding only 3 columns, X, Y, and Z. And I challenge you if you can do it by yourself, by hand. It's impossible. And so they use polytopic geometry and a lot of not easy stuff to construct this example. And they even prove that you can add up to 2n rows or 2n columns, if you have n rows, to make it possible. So not easy proof. But the three mixed equilibria remaining, where you mix between two actions only, cannot be made unique. Okay? So the 3 pure can be made unique, completely mixed can be made unique, but not the equilibria that are mixing between two actions in this example. Okay? Now let's understand why. Let n be the set of players. Sn, the pure strategy set for player n. The index n for play is for a player. Pure strategies profile. Sigma n is the mixed strategy profile, mixed strategy of player I. Probabilities over pure strategies. Six of mixed strategy profile the product of the sigma n. Standard notation S minus n sigma minus n for all players except player n. Payoff vector function G, and the space of game would be, I fix the number of players, the strategies of the players, and I vary the payoffs. It's each point here in R to the power n cross S is a game. Question?
In the previous game, why would you consider the fully mixed one more interesting?
I didn't say that it's interesting. I say it can be made unique. That's it. Okay? It's not interesting. It's even strange. Because it's a potential game, and it's the minimum of the potential. So if all dynamics will diverge from that equilibrium, all normal dynamics, so it shows that not all sustainable equilibria are good. So you should sub-select between them, okay? But that's another question. So we know that -1 are unstable for all dynamics. So to be stable, you should be +1, but it doesn't imply that being +1 is good. This is an example of that.
Sorry.
Yeah.
A question because I got lost. You said the fully mixed is the minimum of the potential?
In this example, yes, because it's a potential game. The completely mixed equilibrium minimizes the potential. So it has less potential than all other equilibria in this game.
It's a fully mixed and it's the minimum of the potential.
Yes. Okay. Okay, let's continue. We have now the equilibrium correspondence, which is the correspondence where for a game and a strategy profile, it's all games and strategy profiles. That strategy profile is an equilibrium of that game. Now I'm going to define the Nash field. So come back to Nash. It's all about Nash in this talk. Okay? Nash field is a continuous map, psi from sigma cross gamma cross sigma to sigma, such that if I fix the game, all the fixed points of the map are the Nash equilibria of the game. So only Nash equilibria are fixed points. So one of the examples is the map that Nash himself used to prove existence of Nash equilibrium. Another one can be the Peirce-Gull-Stackity map. So I take an equilibrium, I take a point sigma I for player I add the gradient of the payoff, which is the vector payoff, because it's a linear game. It's not necessarily in the simplex. I project to the simplex, so it's kind of projected gradient operation. Okay? This map is extremely important, useful for the Goldberg-Mertens theorem, for if you know about this theorem of, and also to show many of the results in game theory. Index of equilibria. So take a game G and psi and Nash field. Take the displacement map, which is identity minus the psi at sigma. All sigma such that d of sigma are 0 are Nash equilibria by definition of psi. And we call an equilibrium regular if the determinant of the Jacobian is non-zero. So it's kind of, you can do the inverse theorem here, implicit theorem here. And the game is regular if all Nash equilibria are regular, and it's known that the set of regular game is open and dense in the space of games. And the index of a regular equilibrium is +1 if the determinant is positive, -1 if the determinant is negative. Index, important. The index is independent of which map you use to compute this index. Independent of the map that was used. Also, index of strict equilibrium is +1, always. You can define index for Nash components. How? You perturb slightly the game. You have a regular game because it's open and dense. All equilibria close to the component, you sum the index, which can +1. The sum of indices will give you a number, natural number. And this natural number is independent of the perturbation you need. Not obvious, but it's true. It can be negative integer, it can be positive integer, and you can be any integers. And there is an example of Govindan and von Stengel on this. Very nice paper on International Journal of Game Theory, I think. The sum of indices over all components of Nash equilibria is always equal +1. It implies in particular if you take a regular game, it has only +1 and -1 equilibria. You do the sum, it's +1. It implies that at least one regular equilibrium is +1. Which gives you existence of a Nash equilibrium of index +1. And the index is invariant, which is a very nice important property. It's invariant to the addition or deletion of inferior replies, and it's also invariant to the addition of a mixture of two strategies. If I take a game and I add a strategy, which is a mixture between top and bottom, as a strategy, pure strategy in the game, it's strategically an equivalent game, but the index of the components containing this equilibrium, because now I may have a component, because I duplicate a strategy, I have a component. This component will have the index of the original game without adding this mixed strategy. So it's invariant to the addition of mixtures. So it's an invariant concept unlike Kalai Samet, persistent equilibrium. So Hofbauer conjecture now, I call it Hofbauer-Meyerson conjecture because it's based on Meyerson's imagination. So some people have a good imagination. A regular Nash equilibrium is sustainable if and only if it has index +1. So the difficulty here, that's the conjecture. Now what happens about this conjecture? It was proved to be true for two-player games by Van Stengel and his PhD student, former PhD student. I don't know if he's still working in academia, but they prove it using.
Sustainable was A3 and A5, just to remember. What you call sustainable was A3 and A5?
No, sustainable is the definition for Bauer. You have two equivalence pairs. Okay? If I can make an equilibrium unique in an equivalence pair, it is sustainable. And sustainable, our definition is you can make it unique by adding inferior replies. And now, what we proved with Govindan and Luca Pal, so Govindan didn't wrote all his paper with Wilson. Some of the papers are with Van Stengel, some with me, and Luca. So we used algebraic geometry to prove this result. For any game, a Nash equilibrium is sustainable, and according to, take any definition you like, if and only if it is isolated. So I didn't specify that the equilibrium should be regular or whatever. It is isolated, and it has index +1. Implies in particular that any regular game has a sustainable equilibrium. Almost every game has a sustainable equilibrium because the set of regular game is open and dense. And there are games without sustainable equilibria. This one is one of them because this game from Goldberg and Mertens, it has only one component of equilibria. It's homeomorphic to a circle. No equilibrium is isolated, so no equilibrium can be made unique. Okay? So the question that comes to mind is how to extend this to non-regular games. How to extend it? So let me show the easy parts of the proof. I will not show the difficult part. Sigma is, let's take sigma an isolated equilibrium. Sigma can be made unique in an equivalence pair G hat. Take G star to be the game where I delete all inferior replies in G. Okay? From the properties of the index is invariant to the deletion or addition of inferior replies. The index of sigma in G should be the index of sigma in G star. Similarly, G star also, by definition of this relation, equivalence relation, is also the game that I can obtain from G hat by deleting inferior replies. So the index of sigma in G star is the same as the index of sigma in G hat. So if sigma is the unique equilibrium, since sigma is the unique equilibrium in G hat by the definition of sustainability, it should have index +1, because the sum of indices over all equilibria is +1. I have only one equilibrium. It should have index +1.
When did you use isolated?
Huh?
Isolated. When did you use isolated in all the stuff you made?
I use isolated a lot.
Where?
Because, so if I take an isolated equilibrium, so when you make it unique, it should be isolated in the larger game. So I didn't use isolated. So I use it where I use isolated.
The inferior replies, I mean, you have to have strictly lower pair.
Yeah, so I'm going to speak about isolated in the next slide. So then you will understand why it cannot be a non-isolated equilibrium, okay? So it will be clear. So since in G hat the index was +1, it should be in the +1 also in the original game. Okay? So that +1 index is a necessary condition was known already by Hofbauer, and this is the proof. The difficulty is to show that all +1 index can be made unique. At least one of them can be, or all of them can be. So what we show is that all of them can be. Okay? So about the isolated question, I got many questions already. It should be counted into 5 minutes. A non-isolated equilibrium sigma. A non-isolated equilibrium sigma of a game cannot be made unique. So the proof is very simple. Why? By contradiction. Let sigma n converge to sigma in the original game. since sigma is the unique equilibrium of G hat, there is a best reply in G hat, but not in G, to sigma n. Not to sigma, but to sigma n, because sigma n is not an equilibrium. Some player has a preferable deviation. Take a subsequence such that this pure strategy is the same for all the sequence n and go to the limit. It implies that this strategy is a best reply to sigma, but we only add inferior replies. We cannot add best replies to sigma. So it's a contradiction. Worse. So now imagine we want to make a subcomponent of a connected component unique. Because we can imagine, okay, let's try to make a subcomponent, strict subcomponent of a component of equilibria unique by adding inferior replies. Can we do that? The same proof shows that we cannot. So if you take a strict component of equilibria, if you can make it unique in a larger game, it should be closed. It's a semi-algebraic set, so it's a closed set. Since it's a strict component of a connected component, there is sigma n in the connected component that converge to our sigma in our component that we want to select. And we use exactly the same argument to reach a contradiction. So if you want to extend our notion to all games, it should be the case that we keep all the components of equilibria. Can we make a component of equilibria unique by adding inferior replies? But this cannot be done in all games because there are games where there is no component of equilibria with index +1. Because it should be the case that if I can make an entire component unique in a larger game, this entire component in the final game should have index +1. So it should have index +1 in the original game. But we have games such that this one, where you have only two connected components. One is +2, the other one is -1. No one is of index +1. So to extend our result, we should go using an axiomatic approach. We will follow the refinement theory literature. We call for every game, we have solutions will be subsets of equilibria. It can be the subset of the Nash component, but it can be anything, like if in Goldberg-Mertens and the refinement. We would like some axioms, existence. Standard axioms are existence in every game, independence of irrelevant alternatives, meaning that if I remove or add an inferior reply to the solution, it should remain a solution, strong form of forward induction. Invariance, adding or deleting duplicate strategies should not change the solution. And essentiality, so now I need to do something, so I would like that if I have a solution and I take a payoff perturbation of my game, okay, I still have a close-by solution in the perturbed game. So these are basic axioms. I add to this sustainability. Sustainability means that if I have a generic game, the unique solutions are what I just defined before, the +1 index equilibrium. Okay, so now I want to extend from generic game to all game using these axioms. What do I obtain if I do that? So I call a game generic if all equilibria are isolated and have or +1 or -1 index. Regular games are generic, but there are games that are generic which are not regular. So there is at least one correspondence satisfying axiom, and it should select among positive index components. It should select among the positive index components. It means what? It means, one, all negative index components are eliminated. Secondly, it doesn't imply that take all positive index components, they are good. One of the reasons is that you have some +1 index equilibria that may not be good. Okay? So to prove this, I will go quickly. We can show that you can add duplicate strategies and perturb such that if you take a negative index component, there will be no +1 index equilibrium close to that component, so it implies eliminate the negative index component. Secondly, you can show that if you take the correspondent that gives you as output the positive index component, this satisfies the axiom, so you have existence. But you can show that if you take this as refinement, you violate the independence, the decomposition axiom of Mertens.
What is the set of games?
All games, finite. All finite games here.
You mean
N-person finite game.
you
Yes, it's multi-matrix because you have n players. N players games where you vary the payoffs of the players. All the games that Nash considered in his thesis are there. So, this concept doesn't satisfy Mertens decomposition, but in the paper, we have a strong sustainability axiom that replaces the sustainability axiom, which reparates this and restore existence by addition of decomposition of Mertens. And the question is how far we can go. I will not explain the O'Neill theorem extension, which is also an open question that was solved. The original question was from Govington and Wilson. We just published this paper in MOR. I can talk about it in another time if you want. So this describes the results. It will take me more than 1 minute. I would like to move on to this first. So, I didn't say about my affiliation is the Moroccan Center for Game Theory. So this will be the world leading center of game theory in few years. And it's in Rabat in Morocco, temperature 20 degrees plus minus 2. We can surf in January, and we surf every Friday with my postdoc who is here. And our PhD program is called Game Theory in Mathematics, Economics, and Computation. So it's exactly the convex combination of the people that are here. And I will be very proud to explain what we are doing there. And thank you.
Thank you very much. We have time for several questions.
Just a clarification. What does inferior mean when you have many Nash equilibria?
What?
What does inferior mean when you have a set?
When you have many Nash equilibria? So what I presented here tells you, if you believe about the independent of irrelevant alternative axioms, and you have many, even infinitely many Nash equilibria, eliminate the negative index equilibria or component. Okay. And keep the positive one.
But by adding inferior strategies?
So it's just adding or dropping inferior strategies is just something about how you imagine. It's like in Arrow's theorem, independent of irrelevant alternatives. So take a game with many equilibria, take one you like, and you ask yourself the question, can I make it unique? I tell you here, yes, if and only if it's isolated and have +1 index.
Okay, I'll ask you in private.
Yes.
So it's inferior relative to a given Nash equilibrium.
It's relatively...
It's given one equilibrium inferior relative to that one.
Actually, I have the same question. I don't really see the link with IIA. I mean, IIA is blue bus, red bus, McFadden. It is not really an irrelevant alternative. It is an inferior one. It's not
irrelevant given the equilibrium. If players should not use it because it's not. So imagine I have a situation, a game, and we have a convention that you should play some equilibrium. Some strategies is not a best reply. At some moment, you may even forget that this strategy was possible in the game, and our game is this game minus this strategy, and we still want that the convention that was a convention remain a convention because something that is irrelevant is dropped. So it's a question of terminology, but for me,
yes,
I think this is the best description.
If you took McFadden's idea of doing the blue bus, red bus, an irrelevant alternative would be still adding the same equilibrium, and just this would still be an irrelevant alternative in the sense of McFadden, right?
I don't know. I forgot about. You should explain to me this McFadden one.
I understand. I agree. I just think that it shouldn't be IIA.
This is a very strong form of IIA. It's very strong form. Yeah.
We're into academic disputes.
So